During this press conference on September 14, 2011, then-Senator Bill Nelson revealed NASA's plans for its next launch system to replace the soon-to-be-retired Space Shuttle.
I'd like to show you what the new rocket looks like. This rocket has a core that is a derivative of the external tank, the apricot-colored external tank. The old external tank would come to about here in the stack of the Space Shuttle to give you an estimate of size. This is the smaller version of this rocket. This is in the range of the 70 to 77 ton. So you can think of the entire stack of the Space Shuttle being about this high. You see the relative size of the rockets.
A simple glance at the vehicle Nelson revealed is a far cry from what NASA is flying today. What has changed on SLS since 2011? Surprisingly, more than one might think, with 2011's SLS being quite different from what's launching 15 years later. We'll start comparing Block 1 version of SLS first, followed by the larger Block 2 version afterwards. One of the most distinct differences is SLS's shift from a Saturn V-esque black and white paint scheme to its current orange colored insulation, appearing to follow a similar path taken by the Space Shuttle external tank back in 1981, when it too lost its paint, and the reasoning is much the same. Reports indicated that NASA saved nearly 1,000 pounds by not painting the core stage. This change was announced in 2015 after the critical design review was concluded. But the differences between vehicles go below the paint and insulation, as the 2011 version used a different aluminum alloy, with plans to be a direct evolution from the Space Shuttle's external tank, something Bill Nelson mentioned in the 2011 announcement.
This rocket has a core that is a derivative of the external tank, the apricot-colored external tank.
But despite plans to build on the original design of the external tank, in 2013 NASA decided to go with a clean sheet design instead, with the core stage being entirely new, including the use of a different grade of aluminum, specifically aluminum alloy 2219. Originally, NASA planned to use 2195, which was expected to be lighter than the 2219 used today. However, due to the larger tank thicknesses and difficulty in welding the more temperamental 2195 tanks, 2219 was chosen instead. The change from 2195 to 2219 reportedly saved up to $30 million in production costs. And yes, you heard that right. NASA made a decision that saved money on the production of SLS. This decision was also aided by data collected during a series of tests in 2011, where NASA built test tanks using the 2195 alloy. The test was the shell buckling knockdown factor, during which they pressed down on the tank with increasing force until it buckled. This allowed NASA to learn the structural limits of the tank's design, which for SLS is critical, as NASA moved away from the horizontally stacked rocket with an orbiter riding piggyback to a vertical rocket with all loads stacked above the core stage. This is the reverse of what NASA decided in regards to the Space Shuttle's external tank, with the first two versions of the tank being known as the standard weight tank, followed by the improved version known as the lightweight tank, with both being made from 2219. But in 1998, through to the end of the Space Shuttle program, they flew with the new super lightweight tank, using aluminum alloy 2195. Moving to the base of the core stage, we can see that SLS initially had 5 RS-25 engines, instead of the 4 seen today. But within a month of the 2011 announcement, NASA had already established that 4 RS-25 engines could sufficiently propel SLS into orbit, so the 5th engine was dropped. But despite being removed from the Space Shuttle, these RS-25s were a new modification to the engines, upgrading their baseline thrust from 491,000 pounds of force to 512,000 pounds of force, an increase of more than 21,000 pounds of thrust per engine. But the upgrades didn't end there. NASA also upgraded much of the electronics and software powering each engine. In fact, I spoke to an individual in 2020 who was working on SLS through the Green Run campaign. He noted that there had been so many changes and modifications to the RS-25s flying on SLS that even if NASA wanted to put them back on the space shuttle to fly again, it would require as much or more work to undo all the changes done to each RS-25, from structural changes to how they were mounted to the core stage, to the aforementioned engine controllers that aren't compatible with the shuttle's computers anymore. Put simply, these aren't space shuttle engines anymore. Before we move upwards, we should turn to what gives SLS the bulk of its thrust at launch, namely, the twin solid rocket boosters, which, despite being visually quite similar to the Shuttle and Ares rocket boosters, had quite a few changes. However, the boosters were mostly placeholders, as NASA knew changes would occur as they were developed for flight.
On either side are depicted 5-second solid rocket boosters, but ultimately NASA will run a competition for these boosters to be solids or liquids.
One major update was replacing the SRB's internal insulation, removing the old asbestos-based material that protected the casing from the burning propellant inside. Each booster now also contains modern avionics in its forward skirt, giving more precise guidance and real-time system monitoring than before. The motor itself was also redesigned to handle higher loads and sustain peak thrust for slightly longer, improving total impulse and helping the boosters deliver more energy and therefore more payload into orbit. Moving up the SLS core stage, we can see the conical adapter known as the Launch Vehicle Stage Adapter, or LVSA. This bridges the gap between the core stage and Block 1's second stage, and uses frangible nuts to split the two vehicles apart. From my research, this stage has changed very little from its early iterations. In fact, there's so little change done to the stage that there's not much to talk about. So here's another fun fact instead. Being stacked atop the SLS core stage, the combined height of the SLS core stage and LVSA is 239.5 feet tall, making it the tallest rocket stage ever built. Ever so slightly taller than even SpaceX's Block 3 Super Heavy rocket booster at 237.2 feet tall. Clarifying that this accolade is strictly in terms of a single stage's height, including all permanently attached structures, like inner stages or adapters, as can be seen in this photo of Artemis 1's ICPS stage, with the first stage drifting along in the background. But as a whole rocket, SLS is still on the shorter side of super heavy launch vehicles. The last component is the upper stage, which for Block 1 would become the Internal Cryogenic Propulsion Stage, or ICPS. Like the LVSA, its design was cemented early on in SLS's development. The earliest reports of NASA using a Delta Cryogenic Second Stage derived stage dates back to around 2012, enabling NASA to jumpstart the ICPS's development and testing, with Artemis 1's ICPS major assembly completing by December 2016, noting that in the early plans for SLS, the ICPS was to be just that, an interim upper stage, with NASA planning to fly the new upgraded upper stage on SLS's third mission. However, due to developmental delays and difficulties with SLS's core stage, the new upper stage was pushed back to what's now known as Artemis 4. But SLS does not end with Block 1. Even in the early phases of SLS's development, there were plans for a more powerful upper stage to try and match or surpass the capabilities of the Saturn V. The 2011 version of SLS Block 2 proposed using an upper stage powered by two J2X engines, whereas SLS's new upper stage, currently unnamed as of the writing of this script, is derived from ULA's Centaur 5 design, evolving to use a commercially off-the-shelf upper stage, much like ICPS was designed to be, with Isaacman hoping this will accelerate production and launch cadence. Prior to this recent change, the upper stage for SLS Block 1B and Block 2 was going to be developed into a more powerful design, that being the dual-use upper stage, sometimes also called the large upper stage, consisting of 4 RL-10 engines and a large open space for co-manifested payloads, similar to how the Saturn V could hold payloads below the Apollo Command Service Module. This stage would be later renamed to the Exploration Upper Stage. The 2011 version of SLS would sport 2 new advanced boosters to replace the existing Shuttle design. These new boosters would incorporate many new design concepts planned for what would become BOL. However, Block 2 wasn't a fixed design and was open to other considerations.
But ultimately, NASA will run a competition for these boosters to be solids or liquids.
For example, NASA was actively considering using liquid rocket boosters developed by Dynetics, who you might remember recently for making the Alpaca HLS proposal for Artemis. Each of these boosters would have used 2 modernized F1 rocket engines. The new modern designs would be known as F1B and began testing in 2013. This isn't a test fire of a rocket engine. This is just the gas generator from a spare F1 rocket engine. After Apollo, it was left unused, and in 2013, NASA used it as a test article to develop the F1B engine. Each F1B engine would have produced up to 1.8 million pounds of force, for a combined thrust per booster of 3.6 million pounds of force, the same amount of thrust as just one of SLS's boosters. But by 2016, NASA ceased interest in the advanced booster competition. As a result, Dynetics wrapped up development on the Pyros booster concept. And lastly, Block 2 wasn't the only other iteration of SLS considered. At an early phase, NASA considered a Block 1A variant, which would see a payload directly attached to the top of the core stage, launching without any second stage, looking similar to the European Ariane 5. But in February 2026, NASA Administrator Jared Isaacman announced plans to standardize SLS development and production, meaning the cancellation of SLS Block 1B and Block 2. While SLS can operate without the exploration upper stage, NASA has a limited supply of Space Shuttle era booster casings, enough to supply boosters through to Artemis 8, but Artemis 9 onwards will not have any boosters to fly with, and being the bulk of SLS's launch thrust, it's a critical necessity. So we await NASA's decision on how they will proceed beyond this issue, potentially resuming work on BOL but without the exploration upper stage, or perhaps restarting the production of Shuttle-era booster casings. It's worth noting that if NASA succeeds at Jared's proposal of 1 SLS launch a year starting as soon as 2026, that would put the last launch of the existing shuttle stock boosters in 2033, long after Jared's time as administrator has ended, meaning it's entirely possible Jared could kick the issue down the road, so another administrator has to deal with it instead. As of writing this script in March 2026, it's unclear how NASA will respond to the limited stock of booster hardware. After I release this video, if a clear plan is stated by Jared Isaacman, then I will follow up this video with a short response to this segment. While most of SLS's changes are in the past, SLS does continue to evolve and grow even between launches. One example is the recent addition of fin-like strakes to the core stage. They were installed in response to vibrations measured between the core stage and the boosters during the launch of Artemis 1. These strakes should dampen and reduce the vibrations and resulting forces on the booster's attachment joints. Another being the recent shift from a new upper stage architecture of SLS Block 1B to the new Centaur-based upper stage. The Space Launch System has evolved in many ways on its road to flight. With SLS being such a long-standing name in modern spaceflight discussions, it's easy for some to miss the details on what's occurred to see SLS launch today. showing that it isn't a frozen vehicle, but like other modern rockets, SLS is constantly changing, evolving, and being upgraded. SLS will continue to change as NASA learns more about the vehicle and what it's capable of.